My name is Sabeur. I'm the Science Director at the IT Innovation Center of the University of Southampton, Department of Electronics and Computer Science. I'm here to give you an overview of the integrated decision support tool that we developed in the INFRARISK project. The tool basically speaks for itself in terms of the term integration. The integration is about the integration of the various heterogeneous databases that you could have access to, as well as the models, results, and information that is needed so that you can have an overview of what's going on in this phenomenon of rare natural hazard and their impact on critical infrastructure. So it is really a decision support tool that would help decision makers. It wouldn't make decisions, but it will support the decision makers. And the good thing about it is that it's a common ground or a common environment where decision makers, in terms of dealing with crises and how to recover from crises and how long it would take to recover from crises, like what has been described by our colleagues in INFRARISK so far, as an integrated information tool. But the challenge is big, but it's not impossible to achieve it. So in terms of IT jargon that we adopted for the INFRARISK IDST, basically we designed the software from scratch, and we started with the aim of creating a portal system, and we chose what we call a Django open source software framework. The good thing about this source software is that it allows flexibility and pluggability of existing databases. We're not going to repeat the creation of databases, and that was good in terms of operational work that we did with our colleagues. And basically, we managed to collaborate with colleagues very flexibly and in a very agile way. So this is what created the software. And from that, we created the services out of it, and we make it available online. The current release, this is the address you can see there, and I welcome everyone to try to access it. So the view of the portal is this way. So it gives the feel of the INFRARISK project and what it does and what is the objectives of the project and so on. All this is facilitated there. Obviously, you have to log in. And you have to go through this, what we call authentication system. There are different types of levels of users, obviously, but in order to come in, you have to have an account, either using Mozilla, Google, Yahoo, or LinkedIn, and so on, or Facebook. Even Facebook, you can do that. So there you go. So this is the facility, so you can log in through that. So you don't need to create your own new account if you have these kind of accounts already, with most people nowadays have. You'll be able to go straight away into the tool. Well, obviously, there are various levels of users, from the administrators, moderators, an author, or someone who just is a member of the public who would like to get access. So depending on their levels, they will see what they could see. So the tool has this kind of field for creating your account, obviously. But I want to emphasize here, what's under the tool is all the challenges that we encountered in the project, basically linking data, linking information, making sense of how to connect data. In order to do that, you have to create what we call an information model, and this model needs to be flexible to be adapted as we go along. But we settled for the one that actually explained the case studies that have been explained so far, and this is now automated. So what we mean automated, machine automated. So the specialists don't need any more to worry about that. They just have to plug in new data if they want to, and the data will be connected automatically through other metadata so that the case studies can be run. So what we have done, obviously the project is contained within 3 years, and obviously we have a contained set of data, but we can go beyond the project and making it more enriched in terms of data support and functionality, why not? But it's all there. So we studied the bridges, the roads, and road sections, and so on, and tunnels. And what we specialize in the hazard data, this is represented by a ground displacement model or with acceleration levels, the PGAs that have been talked by our colleague from UCL and CSEC and so on, and the structural data was more or less focused on bridges, tunnels, and road section, as I said. So this is all data, and then under that, under the IDST, you will have all the relationship between the data there. And this is the work that my team has done to realize the software. So all this wasn't straightforward, but it requires very good collaboration with partners, the knowledge experts in the various fields, and bring it together under a common meta-information model, either for a bridge or a tunnel or a road section and so on. So the runs for the IDRC, you have to create it, you create the particular case and run it, edit it, you can delete it, you can come back to it. These are functionalities as well that are covered. I can go on in explaining the interfaces and the various, the dashboard to create the use case studies. For instance, you choose a particular workflow. So we have chosen the workflow, the overarching workflow that was created by ETSZ and agreed by the rest of the consortium, and we followed that. So there are various steps here in this workflow, and this is automated by machine now. For the case of the Northern Italy scenario around Bologna, like our colleague Dina explained earlier and colleagues, we adopted that for demonstration in the IDST and implementation of the data and so on. So we have this kinds of the definition of the stress test. You have to define your area. You have to give a name to your particular scenario so that you can save it and come back to it in order to provide it to a group of experts to analyze it and so on. You can create as many scenarios as you want. So the spatial boundary is really to contain where you want to study the problem. Again, the system definition, this concept from colleagues were acquired, and it's really understanding what is the system that you're dealing. The system means that you have a particular event, like an earthquake, and then you have the consequences of it and the elements around in the environmental concerned area. So you can also have a facility to choose a particular area across Europe. Identify the source of hazard, for instance, here an earthquake, and you want to see a ground motion hazard and cascading effect triggered by the earthquake. So this is all. I can go live if you want me to, but I want to show you these so in case it doesn't work, if the internet is not accessible. But this is the actual software that we have. You can configure a particular effect of an earthquake, so you give it a value of magnitude, whether high or low activity. You can also give it a number of years return, so how rare it is, and also above which percentile its effect occurs. All these have been described by a colleague. I'm not the expert to explain them in more details, but this is embedded in the software already. Again, you have to choose the particular models to interpret the effect of the earthquake and how the displacement effect. You could have as many models as you want embedded in the software, but in this case, we have two models. We have the ground motion for the bridge effect, ground motion on the bridge and the tunnel. We can't have more because the project is contained by its time and budget, obviously. And also, we agreed collectively on understanding what is damage and the level of damages, and from 0 to 4, basically, effectively 4 types of damage: slight damage, moderate damage, extensive, and complete destruction. And the 0 is just nothing happened. Same thing for the road section and so on. I would like to go very fast here, because this is all. I'm going to take the risk to go live now. Okay. If I fail, I go back to the slides. So let's see. Let's see if I'm not sure. I tried it earlier this morning, and it worked. But okay. It's supposed to be working if the internet bandwidth is okay. So if you go home to here, so here you have the methodology, as I explained, this should go. And the user can sort of query all these steps that it can be taken and so on. These were described earlier by Brian. And if I pick up, you can create, you name your stress test scenario and so on, and you can also save it as well as come back to the saved value as I explained earlier. If I pick up the Bologna case, Northern Italy, I can proceed with this one if it's fast enough, and it gives you automatically the locations and so on. So it's all set up for you, and then you say save and proceed. And then it gives you the boundaries. You can change them if you want. I don't want to do that. And I define the hazards, and I have the earthquake as a choice at the moment. I store it for my scenario, and I have the infrared ground model supporting it, and I can configure the hazards. Here I give, for instance, a high activity and low attenuation, 2,500 years returns, quite rare. I guess I will pick up this, for instance. I store it. This is, okay, this is fast enough, yeah. And now add the network elements. This is going to the databases to pick the data accordingly, as I said. And this is why the meta model works. It gives the automation of where to go. You don't need to go and search it and so on. This is done for you. And so if I view the network elements, there you go. I'm impressed, actually. And here you've got all the elements in the area of northern Italy near Bologna. You've got places, and this gives you the fragility curve that we talked about. I have to choose, what have I done? I have to select the center point of reference so that I can, for instance, I pick this up and make it a central point. And here I can anchor the PGAs that were talked about earlier around it. This takes a bit of time, but hopefully it won't embarrass me. Right. So you got the values of the PGA values for this earthquake consequence, and then you can calculate the damage state if it works. You confirm that you have the databases that you have chosen of 328 elements of bridges and 30 tunnels, and you calculate the direct consequences. And here you have a reporting sort of setup, and you can see the stat of the damage. You've got the DS zeros and 1 and 2 and 3 and 4 and so on. I'm not showing the road section. The road section is quite large, and it's intensively hard to compute it live just now, unless you are patient with me for more than 12 minutes, and this is not good. So you can also download all this information and as a report for your own needs as a knowledge expert. I think I'm done.
Very quick.
Yeah, that's it. That's it. I'm done. This is done.
The final notice, or
I would like to make a point. I would like to thank all my colleagues in the INFRARISK project who worked with us to make this happen, because it requires multiple skills, multiple knowledge experts to bring in people in a very multidisciplinary way to understand how to realize this. This is the result, and I thank everybody in INFRARISK. Thank you.
The GIS knowledge base is basically another software component that has been developed in the INFRARISK project. Basically we tried to come up with a methodology or procedure how to integrate information about major infrastructure failures and natural hazard events. So basically we set up this technical infrastructure to record and help users onboard data about infrastructure failures and natural hazard events. We have done this basically to try to gather and present valuable information on the outcomes of natural hazards on critical transport infrastructures, and potential users of this system that we have developed are infrastructure managers and researchers as well in the area of risk management, transportation, civil engineering, and so on. A particular aspect of our approach is that we based the construction of the knowledge base on something which is called linked data. Basically, it's a modern technology for interconnect disparate sources of information on the web. So the whole point here is that a lot of information about natural hazards and infrastructure components is tabular data. So it's people that have collected, I don't know, spreadsheets or have some databases that can be represented in a tabular format. They are very different in structure, although semantically can be related, and the whole idea is how can we make sense of the data that is represented in tables and give users some sort of intuitive graphical interface that they can consult this data, for example, on infrastructure components and events that occurred on those infrastructure components. So basically our system tries to get you from these tabular data sources or tabular formats into something that is usable by people that are not necessarily technically skilled. So we have developed this knowledge base and a set of graphical user interfaces through which the data can be accessed. So in this example, you see type of graphical interface that we have developed for infrastructure components, where they are and what kind of events or damages happen to the infrastructure components, so that mobile workers can move around and still get quick access to this information. So currently how this knowledge base and the infrastructure, the graphical, the user experience around it looks like. It's basically you get a map and you get locations of either infrastructure components or events that happen on those infrastructure components. You can search this database, you can zoom in, select one of these events that happened here. You can also get this three-dimensional Google Street View on a particular infrastructure component and get information on the events that occurred there. So for example, here you can zoom in on a certain bridge. You have a description of that infrastructure component and some events that happen, whether they caused fatalities, injuries, whether it fully collapsed or not, monetary losses, and so on. So it's an easy way to basically access this information on infrastructure components and events on infrastructure components. Features of this approach that we have developed basically gives you a user-friendly web application to this information. It's grounded on a comprehensive data model for infrastructure components and natural hazards. It provides a mechanism for users that have data in tabular format to onboard, so basically enrich this knowledge base. We have provided hosting access to this data and provision this data as linked data also for developers to use this data. And comes with powerful querying capabilities that allow you to express all sorts of complicated queries on this data. Basically, we started with a number of we tried to build up some sort of controlled vocabulary of people working with infrastructure components and events. So we had a collaborative work in this project where different partners try to agree on terminology and the relationships between different terms and categories of natural hazards and infrastructure components. And collaboratively, we developed what is called a schema or a vocabulary. So basically, starting with all these keywords, infrastructure events, earthquakes, all related terms, we try to structure these relationships between them. Here on the left side, you see a very high level schema, which is a diagram for controlled natural language. Then we documented this schema that you see on the right here. It says, for example, that each bridge is an instance of an infrastructure component. An infrastructure component failure concerns full collapse of an infrastructure component. So we basically try to structure the information that we have in this domain and create this vocabulary. Once we created these vocabularies, We basically collected a set of data samples, for example, data on floods in Europe or bridge failures in Europe, and we tried to connect this spreadsheet or tabular data to this vocabulary. Then we used a tool which was also developed partly in INFRARISK for transforming all this tabular data in what we call graph data, so that it's easier to search, query, and traverse this data to find interesting connections between data entities. So in the end, you go from some tabular format to a set of transformations that generate a graph. So this is a sample of a graph on some sort of infrastructure that has certain importance, high, has some geospatial description, and so on. So we create these graphs out of all the tabular data that are related to infrastructure components and natural hazards. And then once you have this graph, it's much easier to create complicated or complex queries like give me all landslides that occurred in February 2013, giving their dates, locations, and find if any of them result in full collapse of any infrastructure component. So it's much easier now to create complex queries and run them on the knowledge base that we have developed. So to sum up, we have this knowledge base of infrastructure components and natural hazards events. It's based on software that allowed us to transform this tabular data that we had from the project. Onboarding of this data into the knowledge base, we had to perform tabular data cleaning and transforming this data into graph formats. We created transformations for the data and created queries that can be issued against the knowledge base. And of course, you have this fancy graphical user interface that allows you to interact at the user interface level with the data that is stored in this. So I think I've been very quick. Thank you very much.
Thank you very much.